Hello, faithful students. Let's talk about a different special case of projectile motion. My guys have been looking at projectiles that are launched horizontally. And for that special case, that allowed us to define a numerical value of a certain variable. For a horizontally launched projectile, one that goes, from here to there, we said, all right, that's a v initial y is 0 case. All right. This is not that case. This case that we're looking at here, a projectile launched at an angle, this is a special. We'll spend a little time looking at this symmetrical, the case for this symmetrical trajectory. Right? And what we do is we look at an object that is launched at the first instant here at some speed that we'll call v naught at some launch angle theta. What you can see from that little drawing is that, as we've talked about a little bit, it's certainly not that objects move in a straight line and then start to be projectiles. That doesn't happen, right? This vector we've drawn is a representation of this object's velocity at the very first instant in time. Immediately after that, the object's trajectory deflects off that initial straight line path because gravity pulls it downward. Okay? But what is important for us to be able to analyze or make use of, and I'll just rewrite this, is that initially, if we launch something at a certain speed, we'll just call v initial. Well, that initial velocity has components in each of two perpendicular directions that we can call vx and v initial y. Oh boy. You get over there, will you? And you come over here. All right, so it's real important that we recognize and can work with, just because we're given an initial velocity, well, we need to really be able to talk about, and typically launch angles are measured relative to the horizontal. We really are interested in how fast does it move horizontally? How fast is it moving initially vertically? All right? And what you need to be able to do is either think back, my guys, a couple, 3, 4 weeks, 4, 5 weeks, 6 weeks perhaps, or a year or two, and you need to be able to get to this place that, well, let's see, we said sine of the angle here. If I were to redraw v naught y over here, oh yeah, there's a nice right triangle for us. V naught y is, sine of theta is opposite over hypotenuse, and therefore we can write an expression for the size of the initial vertical component of the velocity like that. Similarly, we can use the other, well, another trig function. Well, I guess I can leave this over here and say that if we looked at the cosine of that angle, theta, that would be adjacent over hypotenuse, and therefore the x component of this initial velocity is v naught cosine theta. So believe it or not, my kids, we did this exact stuff a few weeks back, right? And you've definitely done it over the course of your last couple of years in trig or algebra or whatever it is the math folk call it. Okay, so what my hope is that you don't have to recreate the wheel and say, gee, what would happen if I were to find the sine of it? And oh, that's this divided by that. Oh, okay. My hope is that within the next, let's say 24 hours, you can get to this and this place without much thinking. All right. There's nothing wrong with deriving these, but you'll just be spending a little time that might otherwise be more valuably spent doing something else. Okay? That'll be real important for us. Okay. So let us see. Things that we can make use of here, all right? We can make use of a couple of facts. Here's V naught y. Here's Vx. There are really only three places on this trajectory that you'll typically ever be asked about. All right? One of them is here. The reason being, there are nice things we know about that place. And it's convenient, it's typical to say, hey, man, how high might this, hey, man, hey, hey, lady, hey, you, how high might this thing go, right? What's the maximum height it gets to? This is what, a lot of us would call, I don't know, there's a vector delta y max. And at this instant, most of you know, my people definitely know that this velocity, don't do that. This velocity remains, oh boy, remains constant the entire time. So at this instant, it's still going that fast. And then at the end, for that matter, it's still going this fast horizontally. Right? Most of us know that horizontal velocity of a projectile remains constant because what's there to speed it up or slow it down? Nothing. That's what. Okay? I'm just going to, for sake of convenience later, do that. There's Vx. At the top, most of my guys know, oh yeah, we know that the vertical velocity here is 0. Instantaneously, there is no vertical velocity there. Might be better to write Vy instantaneous. Because you could maybe end up calling that your initial vertical or your final vertical, depending on how you want to analyze one of these trajectories. And remember this, folks, this is a symmetrical path, and that tells a lot of my dudes, or a lot of any of you dudes, that, well, it's got the same vertical speed in the end, but just in the opposite direction. There's a symmetry of motion thing. Maybe I'll just move that. Vy. And that tells us that if we've drawn this thing correctly, this trajectory, and I made sure this is a mathematical parabola. I've got spare time. So, ideally, our final velocity looks just like this. And oh man, look at that. Tangent to the curve, just beautiful. Okay, so what I didn't write explicitly was, right, Vy is negative V naught y. I don't know. Those are things that we know. All right. We also know, right, that if this thing takes some total amount of time t to get here, then the amount, well, yeah, say take some total amount of time t to get there. The time to get here would be half the total time. Okay. So nothing too new here. Really nothing new at all. We're just making sure we get back to this. And really the idea that you will never just use a launch speed that's given if that launches at an angle. You will have to use what you know about the launch speed and about the launch angle to find the components of initial velocity in one of these two perpendicular directions. Good so far? Let's proceed. You can't see me make a face when I do that, but I'm making one. All right, so here, let's talk about well, you know what we can actually do. Where do you want this? Over here? Great. We can actually derive right now a formula, an expression for the maximum height that a projectile will reach if it's launched at a speed v naught at an angle theta relative to the horizontal. Now, if you're solving a problem, you're going to do something like this and say, well, what do I know in each of these two directions? I want to know a delta y. Some of you are in the habit, and it's not a bad habit, but from a different kind of problem of saying, well, I have to find time in order to do that. in order to find anything. I got to use the other stuff to find time. That requirement no longer stands for these kinds of problems. You just have to use what you know and you know what you got to look at what you know and what you're trying to figure out. So, I mean, really, what this boils down to is, if we want the maximum height that's telling us something, we ought to say, well, let's call our maximum vertical, or our vertical velocity at the top of this height 0. That's going to be a Vy instantaneous of 0. If I make that the final place on my trajectory, well, then my final vertical velocity is 0. Well, here's the launch speed V0. What we need to know is what V0y is. Well, V0y, the only thing we can say right now is that it's V0 sine theta. I don't know what V0 is. I'm using an arbitrary value, just V0. I don't know what theta is. I'm just saying it's theta. All right, but these things would be true regardless of what values of launch speed and launch angle you got. And of course, you know that A is G downward. Oh yeah, V0y is upward. All right, and so we actually have enough with these 4 things to write one expression for maximum height. So we could, well, what equation has those 4 things in it? Oh yeah, Vy squared is V0y squared plus 2G delta y. If we're saying max height, we have the algebraic, it's not so much of an algebraic luxury, but we can get rid of that. We're looking for delta y, so we subtract V0y squared from each side. That would be 2G delta y, so divide by 2G, and that's delta y. That's delta y max, really. I can hear you through the computer saying, what is V0? Where's the numbers? There are no numbers right now. All right, these are generic expressions for the maximum height that something will go. Oh, I shouldn't have squared this. Yeah, for the maximum height that something will go if it's launched at some speed V0 at some angle theta. What we should do, we should kind of go one more step, probably, and say, well, how do you write V0y? Well, that would be V0 sine theta. I put the squared outside the parentheses now, no big deal. Divided by 2G. Well, that would be delta y max. All right? And the negative is important, remember, because look, G is down, but V0y is up, so they have to have opposite signs. This thing has one sign, and this thing has the opposite sign. That would make delta y max negative, but this algebraic negative turns delta y max into a positive. Oh, goody. All's right with the world, okay? So that's an expression for the maximum height obtained by an object launched at a speed v0 at some launch angle theta. What we're really getting down to here is there could be lots of different maximum heights things reach, but the only thing it actually depends on that could possibly be a variable is this, is how big the initial component of the vertical velocity is. Because g is just g all the time. The only thing it could possibly change is how big this component is. That has all the control in the world on how high things go. So if we say that this is sort of our baseline look here, with this speed and this angle, the question is, well, how high would this one go? Would it go higher or lower or the same height, and how come? So this is a U. In here goes higher, lower, or the same. In here goes your explanation. Higher, lower, the same. Explain. Higher, lower, the same. Okay? Good, good? Thank you. Next, let's talk about how long things spend in the air. Well, so what we would do again here is probably say like, well, let's see, we got some X stuff and some Y stuff. Again, here's our V naught, here's our launch angle theta. Time in the air, time in the air. Well, if we know what V naught is, well, we could define here our V naught Y. So let's say that we have some V naught Y that we could find by just saying I would take the magnitude of V naught and multiply by the sine of the angle there. Clean that up for you. Well, time in the air, well, this is really saying like T total. Remember, there's one thing we know about the full path. We know that over here, there's V final Y. Remember, V final Y is equal and opposite to V initial Y. That's useful. And we know A, of course, is G, and we're looking for time in the air. Well, there's enough just with those four quantities to write an expression for time. Oh, no. Poop. Oh, hey. No. No. Oh, I get it. I get it. How's this going, folks? Good? Good. Hope you're entertained. All right. The X thingy. This is endlessly frustrating. Oh, that's a Y thingy. Okay. What am I doing? Yeah. Finally, all that for that. Yep. So an equation that has those four things in it, Vy is V naught Y plus GT. And check this out. I'm going to write, instead of Vy, I'm going to write negative V naught Y is V naught Y plus GT. I'm trying to solve for T, so that's negative 2 V naught Y divided by G equals T. And remember, V naught Y is up, G is down. So V naught Y and G have opposite signs. That would make T negative, but this algebraic negative takes care of that, so T comes out positive. Of course it does. Right? And, you know, the next little detail is, well, how do we express V naught Y? We write it as V naught sine theta over G. There's an expression for T. So notice again, the time that a projectile spends in the air, if it's a symmetrical one, depends entirely and only on how fast it's fired vertical. G is just G. And that hopefully makes sense, right? I mean, if you want something to spend more time in the air, well, shooting it faster horizontally just doesn't do it. All right, so address the same questions here that you addressed on the previous slide. Okay? All right. Now, next. How far will a projectile travel? Well, this is a trickier one. Because how far will a projectile travel? Well, there's only one equation you can ever use in the horizontal direction for a projectile, and it's this, that delta x is Vx times t. All right, so this one depends, how far something goes depends on two things. It depends on how fast it travels horizontally. But it also depends on how long it spends in the air, and as you know from our discussions 45 seconds ago, the time things spend in the air depends on how fast they're fired vertically. All right? So this expression becomes more complicated. But what I can do, I mean, what you can really end up doing is just saying, okay, let's go back a minute and say, well, I remember an expression for t that's negative 2 v naught sine theta over g. And so I could just say, all right, well, delta x is just vx times that. And then how do you write vx? Well, that's v naught cosine theta. Oops. Times negative 2 v naught sine theta over g. Yeesh. There's an easier way to write that, but I'm not going to bother. That works fine. Why the pause? I don't know. I don't know what to say. Now, here, with this in mind, with this in mind, what I want you to do here is, well, remember, for these, you're going to do this again. And here it goes, farther, not as far, or the same height, or same distance. Farther, not as far, or the same distance. And again, well, not again, but just so we're sure, what I'm talking about here, how far will something travel? I'm talking about this. How far will it land away from where it was launched? What's delta x? So in here we're looking farther, not as far, same distance. And here's what I'm going to tell you. I'm going to tell you that this v naught is of a certain length. This v naught and this v naught are of the same length or the same magnitude. For this one, clearly not the same magnitude. However, I'll tell you that this is a certain launch angle, and this is the same launch angle. Okay? These are going to be a little bit tricky to try to explain, but do your best. This might not be like a real mathematical explanation. It might be like, well, it just sort of makes sense that if this is that size and this is that size, and this would do this but not do that. That should help, right? It doesn't help, but you know how I roll. I think that's it for us. We'll touch up with this stuff soon. Tomorrow when I see you. Oh yeah. Yep. We gotta hunt some monkeys, people. All right. See you soon. So you have stuff to do. Here, 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 here. Thank you. Bye.